All right, well, as a follow-up question, what if we only wanted to visit every landmass in Königsberg? Right, what if we wanted to walk around, visit the North Bank and the South Bank in both islands, but we don't necessarily care about crossing every bridge? That one's easy, right? We can do that for sure. Start wherever you like. Maybe go over this first bridge, the second bridge, then here to the second island and back up to the top. So this is a very simple example of a circuit that starts at the top, visits every vertex exactly once, and returns to the starting position. So in a sense, this is like that traveling salesman problem we had on the warm-up, where somebody's trying to visit every city exactly once and return to the starting position. Right? This is a little bit different from an Euler path because we don't care about using every edge. We just want to visit every vertex exactly once. We call such a path a Hamiltonian or a Hamilton path. So it's a walk in a graph such that every vertex is visited exactly once. And a Hamilton circuit is a graph that visits every vertex exactly once but starts and ends on the same vertex. So you can reuse the starting and ending point only. But otherwise you're visiting every edge exactly once. So we'll look at a few examples here. Do these have Hamiltonian paths? Do they have Hamiltonian circuits, or neither? So in the first case, we can see pretty simply that this does have a Hamiltonian circuit. Start wherever you like, let's say at A. Just visit the outer vertices first. But instead of going back to A here, go to F and then back to A. Now that's not the only Hamiltonian circuit, but they'll all look something similar to that, right? Maybe shifted around, visiting F at a different point. So this has a Hamiltonian circuit. And we can describe it by listing the vertices. We went from A to B to C to D to E to F back to A. Okay, in the second graph, do we have a Hamiltonian circuit or Hamiltonian path, or neither? Well, I think I can see that there's going to be a problem here with this center vertex. Because if we wanted to have a Hamiltonian circuit, if we wanted to visit every vertex and return to our starting point, we're going to have to go through this center vertex twice. Because this section of the graph and this section of the graph are only connected through the vertex 3. So whether you started over here or you started over here, if you wanted to get back to your starting position, you would have to pass through 3 twice. So that tells us that it's not going to have a Hamiltonian circuit, but it could still have a path, and indeed it does. Let's say we started at 1, then went to 2, then 7, then 3, then 4, then 6, then 5. That would work. So we would have 1, 2, 7, 3, 4, 6, and 5. Right, and a similar thing happens down here. This is almost the same graph, but with 2 little extra pieces at the end. And so yeah, we could still go from X to Y to Z to U, right? The same basic path, but with these extra points here at the end. Now, what if I were to add 1 extra vertex and edge, say down here? Does this have a Hamiltonian path still? Well, think about it for a second. So it does not, right? So the issue here is if we were to start either at X or at, what should I call this? Call this Q, or at R, you would be able to visit one of the other single degree vertices, right? These all have degree 1, but you wouldn't be able to visit both of them, right? Let's say you started at X. You could start going for your walk, make some choices here, but either you'll eventually hit Q first, or you'll eventually hit R first, and whichever one you hit, you won't be able to leave without repeating the vertex that you came from right before. Okay, so this is an example of a graph that has no Hamiltonian path or circuit. Now remember, with Euler paths or circuit, we had this nice result that said, just look at the degree of every vertex and figure out, does it have all even degrees, or does it have exactly 2 odd degrees, or neither? And it was a real quick way of checking whether a graph had a Euler path or circuit. Unfortunately, for Hamiltonian paths or circuits, it is not that easy. There is no known quick way of figuring out whether a graph has a Hamiltonian path or circuit. So for us, when we're looking at smaller graphs, we just have to guess and check. We have to play around with it until we can convince ourselves that there isn't one, or until we can find one. But for a very, very large graph, this is a difficult problem. Computationally, it's very difficult. It's one of those NP-complete problems if you know anything about computational complexity. So that's a much harder problem to do. So it seems like it should be a little bit easier because you don't have to visit every edge, you only have to visit every vertex, but in fact, turns out it's a computationally very tough problem to solve.